Okay, so in this lecture on graph visualization, I want to talk about the visualization of non-spatial data, specifically non-spatial data that capture relationships. So we are familiar with such structures. These are trees, graphs, networks, and so on. So the idea is to, in this lecture, to give an overview of different techniques for visualizing such graphs and networks, and the special case of trees. Rather than talking about one or two techniques in great detail, right? However, I will talk about a few techniques, describe them a little bit more than the others, so that you get an idea about so that you get some kind of an understanding of these techniques and what it means in terms of the design of the technique, in terms of its computation time, in terms of its usability, and so on. But the overall goal is for you to get an understanding of what are the different techniques available out there for graph visualization, for tree visualization. And also with the reference, you will be able to go and look up this collection later when you need it, right? So several of these techniques are already implemented in existing visualization software, or there are projects or that's code available that you can quickly integrate with nice modular libraries that support graph visualization. So I'll talk about them a little bit more, and we will cover some of these again when some of you as project teams present or give demos about these visualization tools. So you will notice that graphs will play an important role in some of these visualization tools as well. So since many of you are, since all of you are here in the session with me, feel free to ask questions during the talk, right? So the plan is this. I'm going to start by talking about tree layouts. We did cover tree visualization techniques a little bit in the previous class, but our focus was primarily on one technique, which was TreeMap. Here I'm going to give you more like a menu of different techniques that are available, right? We will not be able to eat everything in that menu, so we'll be able to sample only a few because of the time limitation. So I'll do the same for graph layout and visualization. Personally, I like to distinguish between the term layout and visualization. A layout refers to simply an algorithm that decides how to place the nodes and the edges in the graph or the tree. Whereas when you say visualization, it refers to the layout together with interaction capabilities, together with an analysis of how useful this technique is, and so on. Right. So the term graph visualization or tree visualization is much bigger than just a simple than an algorithm for laying out the graph or the tree on the plane. What I'm going to cover today is primarily from a survey that came out some time ago by Herman et al. On graph visualization. There are these techniques are that I'm going to discuss today are already popular and they have been used. You must have seen some of these techniques already, either in like popular media, if you have looked at articles on let's say Medium and so on, or if you have looked at newspapers and looked at their statistical graphics, you would have already seen some of these visualizations. But you may not know their names and maybe now is a time to know the names of these techniques. Let's begin with trees. Let's begin with the example that I used in the previous lecture as well. Looking at files and their hierarchy in your computer. Right? The first question to ask when you want to design a visualization or a layout is, what is the purpose? Why am I creating this visualization? Right? What are the tasks that I would like this visualization to support? So naturally, one task is that you would like to navigate through the hierarchy of your file structure of your folders, and possibly to find a particular file. There are two common problems that you come up with while performing this task. One question that you ask, or one problem is, where am I in the file structure, right? In the file hierarchy. And the second is, where is the file that I'm looking for? To answer the second question, of course, we have much better tools now, search-based tools. You just type in a query and then you exactly find the location of your file. But you can imagine situations, you must have come across such situations where you don't remember the exact file name, right? And maybe you know that the folder contains multiple files with similar names. So you type in that query and then you go to the appropriate folder and then search in that neighborhood, right? So a search-based query cannot always give you the answer for finding a particular file because you may not have the appropriate query. So visualization still plays a role. And you use this day to day, so hopefully you can relate to it. A good way of visualizing the folder structure goes a long way in locating the particular file that you care about. Excuse me. So I'm going to go back to this cascaded list. This what is shown here is called the cascaded list. That is common on the Mac. It's a wonderful visualization design, and I will talk about it again when we come back to it. This allows you to answer these questions, the two questions, very easily. Just because you visualize the different levels of the hierarchy in columns, you are able to quickly answer the question, where am I? Because of the highlighted folder and the file. And since you see the list of files in the last column, you also are able to find the file that you're looking for. There may be other kinds of tree structures, ones which are more rooted, such as an organizational chart. And the questions here may be an overall understanding of the organization. Is it a flat or a deep hierarchy? What is the reporting kind of structure? Who reports to whom, right? If you are, for example, one of the managers, who do you report to, and what is your path towards the president or the director of the organization? Tournaments provide another kind of tree where you have this is often binary, not necessarily, but often binary. And there is a clear level structure. Often these are complete trees. And the kind of queries you have here is much different. You want to know at every round who are the teams that have competed and who have won, and so on, right? So that's another kind of tree. Family trees is quite different. Again, the kind of queries you may want to ask is, of course, simple queries such as who is a common ancestor, and how close are two different branches to each other within the family, and so on. Evolutionary trees are similar to family trees, where you want to study how different species evolved and diversified into the modern day species. So these trees are also studied uh, within the scientific community. Trees can come from different disciplines. Um, if you are a DIY fan, right? So if you would know the benefit of such an assembly instruction, which clearly tells you what is the order in which you want to um, assemble the different parts so that you can so A, to do the assembly efficiently, and B, to do it without going back and forth, right? And while always having the big picture in mind, right, as to how all these parts will fit together to form your. In this case, I'm not sure what this part is. It looks like a lathe, but I'm not sure. So there are several types of trees. That was what I had talked about so far. What are the approaches for tree visualization or tree layout? Let's talk about layouts first. There are three types of layouts. One is called the node link diagrams. As the name suggests, these are layouts where you use some kind of a glyph, like a disk or some kind of a shape to indicate a node, and the links are links between these nodes, or arcs between the nodes, are represented as edges or as curves. There are different techniques. We will quickly see examples of these techniques that fall under the node link diagram. Another approach to tree visualization is to capture the hierarchy in the tree via enclosures. So we have seen this already, tree maps. There are versions of this tree maps called Voronoi TreeMaps. We'll see an example. And other ways to capture this hierarchy via enclosure, something called jigsaw maps and so on. And there are completely alternate approaches. We'll see a few examples that have been designed to kind of efficiently support certain tasks. We already saw the cascaded list from the Max file browser called the Finder. There are a few more techniques that we will see called the Icicle Trees, and the polar version of that called the Sunburst Diagrams. Some of these names may already be familiar to you. Like I said, if you have seen statistical graphics on newspapers, particularly newspapers that have good kind of graphic teams, a few that are really good are the New York Times. I think the Washington Post also had a few. And now during COVID times, there are a few web pages or dashboards that have done a great job. Within India, there was COVID-19india.org, which had state-of-the-art visualization techniques on top of the rich collection of data that they were presenting to the user. So let's jump into the different node link diagrams to begin with. Here is the most simple of them all, right? This is called the Reingold-Tilford layout. So this is a top-down layout, quite simple. Let's just understand this a little bit, right? So the layout is as follows. You start with the root node and position it at the top or the left center, depending on whether you want the layout to be top down or left to right, right? Whether you want to use the vertical axis or the horizontal axis. Now, Once you position the root, um, you essentially draw the left subtree on the on this half plane, and you draw the right subtree on the other half plane, right? So you have essentially or recursively posed the problem as positioning the root followed by deciding where to position the left subtree and the right subtree, right? So it's a recursive algorithm. Nothing surprising here. The only key question to answer is, where do you position this root, right? So the way you identify that is by looking at the size of the left subtree and the right subtree. So you allocate space that is proportional to the size of the two subtrees. So in this case, I think the left subtree and right subtree have more or less equal number of nodes, so which is why the root is positioned more or less on the center along the x-axis. Now, after this, what is done is that you, like I said, you recursively look at the left subtree and the right subtree. So for the left subtree, you again have to decide where to position the root. You notice that the right subtree of this node, right? So let's call this V, right? Or V sub 1. The right subtree has only one node, whereas the left subtree is large, right? So you allocate appropriate space and position the node such that significant space is available for the left subtree, and very little space is allocated for the right subtree, right? And again, do this recursively. So it's a very simple algorithm, but let's analyze this a little bit more. What does it do? How does it map the different aspects of the tree to the dimensions that are available, right? So you are drawing everything on the plane. So there are two dimensions, like I said, the x-axis and the y-axis. You can call this as the breadth and the height and the width, for example, right? So the x-axis corresponds to the width, and the y-axis corresponds to the height, right? Now, so this is the width. Now the tree has a few dimensions on its own. One is the fan out, which is called the breadth. The fan out is the number of children at a given node, right? There is another property of the tree, which is the depth, right? So the question now is, how do you map the depth and the breadth to the two dimensions that you have on the plane? So what the Reingold-Tilford layout does is, it takes the breadth and maps it to width, which is x-axis, and it takes the depth and maps that to the height axis, right? So very simple, and it creates a layout such as this. It's easy to see the hierarchy and so on. But you can quickly also talk, it's common sense to quickly talk about the disadvantages, right? While the careful choice of your root node allows you to spread out the nodes along the width, this particular layout does not make good use of all the area that is available. For example, there's a lot of area available on the top left and top right, which has not been used. There's a lot of empty space, right? So it does not efficiently use space, but it does capture the hierarchy, right? So I'm trying to go through these aspects in a little bit more detail for this layout, but you can try to do this exercise for the other layouts that I'm going to present, right? So just to recap, what did I say? I talked about how the different dimensions of the tree are mapped to the dimensions on the plane. And I talked a little bit about how well does the layout utilize the space, and how well does the layout allow you to interpret the different dimensions, right? So these are the questions that you want to ask when you see a new layout. Okay, so there is a simple variant of this layout where you go from the Cartesian coordinate system to the polar coordinates. So a similar tree, if you use instead of the height and width, if you use the angle and radius, then you have what is called a radial layout. So here the root is located at the center, that is A, and the breadth of the tree is mapped to angle. So what this means is if A has a few children, they are all located on a circle centered at A, and the sector associated with a particular node, right? So the sector associated with a particular node is proportional to the size of the subtree that is rooted at that child. Okay, that's the idea. So you can position the nodes, the children of A along this circle that I have indicated here, and each child gets a sector. So hence breadth is mapped to angle. The depth is mapped to radius. So children of children are located on the second concentric circle, right? Such as this. Children of children of children are located in the on the third concentric circle, and so on. Right? So hence depth is mapped to radius. So this is the radial layout. There is the Microsoft's indented layout for folder structure. So what this does is it places all the elements on the vertical axis, right? And the way it shows the parent-child relationship is via an indentation, one tab indentation or so, right? One criticism here is that the breadth and the depth end up fighting for the same height resource. Breadth is mapped to height and to locality. Neighboring children lie close to each other, but the breadth is also mapped to the height, to the vertical axis. The depth is also mapped to height, even though we use indentation to figure out the depth, but it also uses up the height dimension, right? So in that sense, the Microsoft File Explorer maps the two different dimensions of the tree to the same space dimension. Okay, there are a few, I don't know what's the term to use, fancy techniques that were tried out in the early days of tree visualization when people tried to use graphics for everything. These were failures because they tried to use 3D and other realistic renderings when there was no need for them, right? So here is one example called the cone tree, which uses the 3D world, and the root is here. For example, the MS Office is the root, and all the children of this root are placed on a cone whose apex is the root. So if you can't see it like that, so there is a cone centered at that root, and all the children are positioned along that cone, right? And then you do this recursively. So this is the idea. You do this in 3D. Now the shadows of these are shown on the floor. These look like triangles. Each cone projects onto its shadow, which is a triangle. and you see the shadow shows some kind of a additional structure about the hierarchy. This was a failure because there is a lot of occlusion. You don't get to see the entire file structure, the hierarchy, and so on. There is a variant of this called the balloon tree in 2D, which is quite efficient and is used. The idea is this. Unlike the radial layout, where you use concentric circles to map nodes from every depth, what you do here is you take the root, which is at the center, and you have its children are positioned on a circle centered at this node. The children of those children are positioned at a circle centered at the corresponding node, right? But they are located close to that child. So if this is U, its child is V. V's children are positioned around it, right? So in that sense, you use space quite efficiently. You know whose child is whom. So this is used in multiple applications. So these are just the flattened versions of the code tree. Hyperbolic space allows you to find out the positions of these nodes and at different levels quite effectively. So one of the early uses of this hyperbolic space, so hyperbolic space allows you to so it allows you to deform the edges and their lengths because you don't have straight lines anymore in this hyperbolic space. So once you project that onto the plane, of course, you can't draw everything in the hyperbolic space because we want to show everything on the monitor. The hyperbolic space just allows you to find the locations of these different nodes and their children. So this was first tried for example, AT&T tried to use this to show the different connections via telephone, and in later days, communication networks. So you can project this down onto the plane, and unlike the balloon trees where you are forced to show all the nodes on a circle, here you can use this hyperbolic space to so as you can see here, the nodes are not necessarily positioned on a circle, but they are positioned on this curved space, right? So it allows a better use of the entire area that's available. So there is a version of this developed by Tamara Munzner. If you recall, Tamara Munzner was the author of that the book that I talked about last during the previous lecture. Tree maps. So moving on to the second approach of nested hierarchies. So tree maps provide a good way of visualizing trees. There is a variant of tree maps where instead of just using rectangles and nested rectangles, you can use the ideas of what is called a Voronoi diagram, which is a more efficient way to partition space. So the space is partitioned in a Voronoi diagram depending on the weight of that particular point. So if you look at the figure on the left, you have you can imagine that this is you can look at this triangle, and the triangle is decomposed into these few regions that you can see at the first level. So that's already the second level. There is this, right? So you can see these. So you can imagine that there is a point within each region of the triangle, and there is each of these points carry some weight, and the region associated to that point. So let's say there is a point here, there is a point here, and there is a point here. The weight associated to each point is proportional to the distance from that point. So every point captures some region. right? So every point you can imagine that is tries to capture regions around it, and it captures all the regions that are closer to it than others. So for example, this point V will try to capture all the points that are closer to it than from U and W. Right? So this will give you a polygonal region centered at V. Similarly, U gets a polygonal region centered at U, and W gets something like that. Now you can do this hierarchically, and so you get a recursive structure. This is called the Voronoi tree map. And you can do this on a circular, like on a spherical domain as well. Right? So this was introduced much later and found to be quite useful. Um, uh, Adjacency relationships can be displayed using something called the Icicle tree. This is quite popular. You may have seen this. So the edges in your tree are implied by the adjacency between the blocks. So here the cyan block on the top is the root, and there is an edge between that block and the blocks on the next level because they are adjacent to each other. So the Icicle tree shows hierarchy and also the how balanced the tree is and so on. There is a radial version of this Icicle tree called the Sunburst diagram. This is quite popular in the biology literature to show different biological networks. Okay, so the third approach, like I said, is a kind of a miscellaneous collection. One of them is the cascaded list, which uses a combination of what we saw earlier. So one of the dimensions, the height and width, are used to indicate the tree's breadth and the depth. But in addition, you partition the space into columns so that you can show all the folders within that particular depth, right, in detail, and it allows you to browse through that level in good detail. So this is quite a useful structure, especially if you want to explore all the folders and files and so on, right? And you want to go back and forth in your hierarchy. So one natural question is, what technique should I use? Right. So there is no one golden recipe, but this is one of the most challenging questions and often used, often asked questions. So there is a crucial decision to be made because the technique that you use could determine how quickly you find what you're looking for. While making this choice, other than in addition to the different issues that we talked about, right? So utilization of space and analysis and so on. You may want to keep in mind that the computer's interaction with the human is quite important, right? So the human makes the final analysis. So how the human interacts with the visualization is quite important. So in that sense, you do want to pay enough attention to the method, but you should pay enough, a good amount of attention to the user and think about how they are going to read your visualization. So in some cases, you don't want a fancy visualization. Like I said, for the cone trees, this was a failure because this was fancy, but it was not useful really. If you have simple enough data, maybe just a simple bar chart or even just text should be enough, right? So people do read quite fast. They are able to scan in lines quite quickly, right? You also have to be mindful of the convention, right? So let's say you are going to become a data analyst, right? That's probably one of the situations where you will be required to display your output as a tree or a graph or as a matrix or simple charts, right? You need to know what is the convention in that particular application domain. So biologists may already be used to presenting their data in a particular way using specific colors. In the case of, let's say, you're doing business analytics data, then again, depending on the application domain, let's say it's stocks, then people may be using a particular representation for indicating up and downward progression. So you have to be mindful of that, right? You have to augment that rather than do something quite different. So I talked already about how much real estate or screen space you are going to occupy. So if your tree is going to occupy only a small amount of screen and much of that is white space, then you're not doing a good job, right? So you need to be careful of that. And oftentimes a simple solution is always good. Okay, so with that, I will move to graph visualization or graph layout to begin with. Graphs or networks are a completely different, they present completely different challenges. So by the way, I want to remind you again that if you have questions, do ask. So the challenges that graphs bring in is that you don't have this natural hierarchy. You don't have the different depths. It's not clear because you have cycles, and there is a lot of the amount of connectedness is much higher than in a tree. So there is no natural way to lay out the network. Traditionally, graph drawing tried to optimize a few criteria. For example, they try to reduce the number of bends that you use to show an arc, like what you see on the top left. You don't want to show curves because that's difficult to draw, so you want to show them as polylines. Why do you need polylines, not straight lines? Because if you use straight lines, there will be a lot of crossings, and crossings make it difficult to interpret the graph. Right? It also leads to a lot of clutter. So that's why you need polylines or curves. One additional criterion people try to bring in is try to use only horizontal or vertical line segments, like the one you see on the top right. This is like this is called an orthogonal drawing. You can try to pose a constraint that you want only straight line edges and still try to reduce clutter. So this is shown on the bottom left. If there is some hierarchy, you want to highlight that in your graph. So for example, if you have, let's say you have the flow graph in a program, there is a natural direction. So you want to show that in your drawing, right? So there are different, these are simple characteristics or simple properties that you want to satisfy while coming up with a drawing.
Sir.
Yes.
In the previous slide, so there was the orthogonal drawing. So here I can see that if from a node there are lines coming, I mean edges coming out. So here it is tried to, I mean edges should not overlap. So I mean here it is tried, I think. So if a node has more than 4 edges, so how it can be represented here?
Okay, that's a good question. So I think the number of edges is not so. The number of or the valence of a node is not so crucial. It is the total number of edges that is crucial here, right? So we know that if you have a graph with n nodes, right? Then if you have more than n minus 1 edges, you know that there are going to be cycles, right? And there is no guarantee that the graph is going to be planar anymore, right? So one criterion that people often try to optimize is to reduce the number of crossings, right? So the number of crossings is dependent on the total number of edges, not so much on the valence of a particular node, right? So of course it depends on the average valence and not necessarily the maximum valence or the maximum degree. Does that make sense? If you have more edges, you have more chance that the graph is not planar, right?
Yes.
Yeah. Okay. So in the traditional graph layout algorithms would set these criteria, for example, orthogonality, number of crossings, and so on, and try to optimize these criteria. So these criteria were called aesthetics. They were called mathematical aesthetics because the description is motivated by aesthetic drawing. So you want fewer crossings, you want orthogonal. So these improve the aesthetics of the drawing, but they are mathematically stated. So that's why it's called mathematical aesthetics. So for example, like I mentioned, edge crossings or reduce the area that is used for the drawing, or reduce the angle and so on, right? If there is symmetry in the graph, then you show that and so on. So you try to optimize all of them. It's not possible to optimize all because there is often a trade-off. So if you pose this as an optimization problem, then the solution, there is no tractable solution. There is no polynomial time solution often. And approximation algorithms also turn out to be quite complex to design. So the practical solutions are often greedy or based on heuristics. Of course, if you have a graph, a fixed graph that for which you want to compute the layout only once, then you can run this kind of a brute force approach and prepare a layout and you're done with it, right? But that's not the case. Often these graphs change with time and you want to recreate the visualization and so on, right? So while this approach is good and useful, it does not scale to large data sizes or large graph sizes. There are multiple approaches that have been tried for graph layout, followed by visualization. So I'm going to talk about 3 or 4 of them here. The first approach is to reuse what is known already. So try to what's called treeify a graph. So find some natural root and find a hierarchical representation of nodes in the graph. In that way, you are converting it into a tree, and then use tree layout techniques. A second approach is if you can just find hierarchy, then you don't necessarily extract a tree from the graph, but you just highlight that hierarchy. Then there are generic optimization-based techniques and a few additional kind of out-of-the-box thinking type techniques that I'll talk about at the end. Okay, so like I said, the first idea is to reuse what is known. So we know how to lay out a tree, and we are given a graph. So the first solution is convert the graph into a tree, right? Of course, when you convert a graph into a tree, you lose some information. So what are some ways to convert? You select an important tree structure within the graph. For example, the breadth first search tree or the spanning tree and so on. Right? Or it can be one tree, it could be a collection of trees. Right? And then you use your favorite tree layout algorithm to display that tree and optionally show the additional edges in the graph. The benefit is you are reusing existing work, and we know that the tree layout algorithms often work much faster. So computationally, you are good, and the tree layout techniques also support interaction and so on. Of course, the drawback is that you're not showing the graph as it is, you're showing only a substructure, right? So you're limiting the type of layouts that you can generate using this approach. Like I mentioned, another approach is the hierarchical approach, where you try to come up with a hierarchy from the graph and you show the graph as it is with the hierarchy. This is not always possible. But for example, if you have something like a DAG, then maybe this is possible, right? There are several applications where you don't have a generic graph, where you don't have cycles and so on. So it is indeed possible to come up with a hierarchical presentation. Tracking graphs is an interesting example. And here, the example here is the evolution of different versions, in this case of Unix. You can imagine the version control graph is another example. It's very similar to the graph that you see here. Okay. So the second approach is, or rather third approach is generic optimization, where you specify all the constraints for the layout. So these are all series of mathematical equations. Each equation is kind of relating the position of one node to the position of other nodes, right? And you hand it to a solver, which tries to find the optimal location of all the nodes on the plane, satisfying the constraints that you have written down. Like we saw earlier, there are different constraints that you can impose, right? Different distances and so on. We look at one or two examples. This is the advantage is that this is general. You can use this for any application. So it's like one big hammer that you can use anywhere. So one benefit is that you can customize it. You can add constraints that are specific to your application domain. So that's one benefit. It's a generic framework, but of course the same benefits also act as drawbacks. So while the technique is general, it is often too general and you may not get the required layout. Solving the optimization problem is a big problem. So computationally, you have a slow solution. And the final look that you get, the final layout that you get may not be easy to interpret because you are using a generic technique. And even if you change one parameter a little bit, the output changes dramatically, and it's very difficult to make sense of this. One approach that's quite popular is the force-directed layout. This is something you should have seen. There's a lot of visualizations available like this. The force-directed layout uses a physics metaphor of mass and spring. There is a mass associated with every node. There is a spring associated with every edge. The masses, the spring constant of the edge forces the forces the nodes to come together, right? So there is a spring, so you can't push the nodes far apart because there is a spring connecting the two, so it will bring them closer. But the masses at the nodes will also, you can think of them as charges, and they will repel each other. That's one way to think of it. So this trade-off will give you a good layout. So the layout will ensure that nodes that are connected to each other will lie close to each other, and nodes that are not connected will lie further away. Right? So of course, the final layout depends on the initial condition here. The solution is often iterative, and there is no one global optimum. So this is the solution. The solution is fast, but it is iterative and greedy. And this is used often. So one benefit is that you can allow the users to interact. So the user could, for example, move one of these nodes if they know that it should not lie there. And then the method will compute a new local optimum. right? So this is called the force-directed layout. There are approaches that begin from this idea and improve it. The Dickola algorithm is one such. This is called the directed graph constraint optimization layout. So what it does is it first of all identifies hierarchy in a coarse manner, and it uses this hierarchy as a constraint, and then calls a optimization-based layout, such as a force-directed layout. So the nodes don't have the freedom to go wherever they want. They are restricted to some hierarchy, to some levels, and within that they can move. So unlike the what is called the Sugiyama layout on the left, so there is a popular graph drawing tool called Dot. You can go and take a look. Dot is one of the standard graph drawing tools. It's available from graphviz.org, and if you just search for Dot, you will get this. So this presents the graph in using a hierarchical layout, but as you can see, it does not use space too well. The Dickola starts with the hierarchy that is identified with the Sugiyama, and then allows for a more relaxed layout, that thereby using the space better. And of course, in this case, it also preserves the lengths. All the lengths, edge lengths are kind of equal. That also allows for easy interpretation. Okay, so finally, I want to talk about some of the techniques that are quite different and hence were not explored in the initial days of graph visualization work. So we have looked so far at node link diagrams primarily and a little bit at nested hierarchies. These don't scale too well. If you have large number of nodes or large number of links, then you end up having a lot of crossings, a lot of occlusion, and it's difficult to read. There are solutions to this. One solution is to reduce the number of nodes, build a smaller graph, what are called spanner graphs, and then look at those smaller graphs. Another solution is to use alternate representations. We know that a graph can be represented as an adjacency matrix. We know how to display tables or matrices. The idea is to use that matrix to understand the structure of the graph. Right? So you show the adjacency matrix as it is. So the cells are the edges, right? And we know how to show large matrices. We can cluster together different nodes so that they form a single column and a single row. Lots of other techniques that we can employ from simple image-based techniques, right? So your matrix essentially becomes like an image or a heat map, and the color indicates the edge, whether the edge exists or not, together with maybe the cost of that edge or the weight of that edge. Clusters here indicate the presence of cliques in the graph. You can reorder the columns and rows to understand the different connectivity structures. What you see here is also an interaction technique using something called the fish eye lens. So it's like a magnifying lens that you can move over the matrix. So the magnifying lens shows you the local structure in detail. So this is one way of interacting with your adjacency matrix representation. This is quite popular. There are variants of this called small multiples and so on. There's a lot of work done on this idea. Another completely different approach is to just ignore the connectivity structure and show the graph as it is with the nodes, but use the attributes of the data to identify the layout. For example, if you have geography data, you use the geographic locations to just position the nodes and then show them. the layout is very easy to compute. And in some cases, it's easier to interpret this graph. Of course, it doesn't show the connectivity so well in some cases. One simple example is this internet connectivity graph, where the angle just shows the longitude or the geography of the particular IP. And the radius, I think, indicates the degree, the number of connections. So it's called the skitter visualization. Right. So there are several approaches. I have only given a kind of a small sample here. But hopefully this introduction helps you kind of get a flavor of the techniques that are available out there, and also gives you an idea about the questions you should ask if you want to choose one visualization technique. Often you don't have to invent a new visualization technique if you have a medium-sized data. You just have to know enough to identify one of the existing techniques. Right? So I'll end with that, and I'm happy to answer questions now before I stop the recording.